Hi, Mr. Cohen. Can you hear me?
Yes, I can. Hi, Connor. How are you?
I'm good. I am, well, I guess I'm okay.
All right.
I am still working through. I struggled on one of the questions that was the difference quotient questions.
Okay.
But I think I'm not quite sure how much of it is actually not me getting it as opposed to what they're expecting the answer to be. Or maybe those two kind of cross over.
Are you beyond limits? I want to make sure we didn't really spend a whole lot on evaluating limits. There were a couple other. I told you about the factoring method, and there's a couple of other methods that you need to know. But if you're on to the difference quotient and you're into differential calculus, then let's go there.
I think it was the last two problems on the homework, so I don't want to say that I'm quite there. She is. It's funny because when we had the tutoring session, you had shown what the derivative looks like and how to do it, and then I watched my teacher's video of the class for Tuesday or Thursday of this week. I can't remember which one. So, but either way, I watched her do a derivative in her head, and I knew that's what she'd done. But she's not doing that in class.
Okay.
So we're not really there. I think she's, it's the next one or two sections. It's got to be because.
I suppose the best thing we can do is tackle your problems.
Yes.
If there's a couple of problems that you didn't know how to do, let's look at them.
Okay, so this is kind of ambiguous, but this is, and I'll explain. So it starts off with an equation, and it's 3 sine of 2t plus 2t, and then at t it's -1. And so the question asks, this is like a.
Hold on. Oh. You said this was an equation. I missed the equal sign.
KT equals that, what you have there. Or K of t, I should say. K of t.
So we have a function of t that equals that.
Yes.
Okay. Cool. Now what's the question?
So now this, so now the question asks, what's the average velocity over the intervals given? And bear with me. And then it says use it to approximate the instantaneous velocity.
Okay. So what are the intervals given?
Well, this is the thing. I guess there's two ways to look at this. There's one that's at. So let me just say this. So it's 1 in 0.0996.
Okay.
And then 1.5 and 0.2, or I'm sorry, 0.0222, 3 twos. And then 2 comma 0.550. And then 2.5 and then dot 0011. Technically, the way this question looks, Mr. Cohen, this is 1 sub c, and it actually only just gives you the equation. So I wasn't sure.
That's fine.
We can just
trying to do here. Your entire math career has been based on average rate of change. In other words, if I gave you a curve and I said, what's the average rate of change between that point and that point? You would take, let's call that A, let's call that B. This, therefore, is f of b. Very important you understand this terminology. In other words, that point right there is f of a, and that point is f of b.
Okay.
It's critical to understanding calculus, that you understand function notation.
Yeah, agreed.
Okay? So all of these questions are basically saying, what's the average rate of change, which is the slope?
Right.
That's what they mean.
Right.
So what they're really all saying is f of b minus
f of
a
over
all
a
over, no,
b
all
minus
over
a.
b minus a. Remember, this is the rise.
And that's the run.
That's the run. So every one of these is just substitution. Okay?
Okay.
So if we look at the first interval, what is, we'll call, I'm going to call that A and that B in each of these cases.
For all the intervals.
Yeah.
Yeah.
And the other way you could look at it is the first number is B and the second number is A.
Mm-hmm.
And that will give you, I don't know how they mean it. Usually you're going from low to high. All of these go from high to low. But what that means is we have a negative slope. Okay? Maybe. So, if we want this first one right here, then substitute it in. What is f of b? In fact, here, let me do this. Just substitute it in.
Okay. So so f of b in this context is 0.0996.
Hold on. Let's substitute first before you give me a number.
Sorry.
In other words, well, this is pretty important actually, because this tells you how you got that number.
It's 0.0996. Okay, plus 2 times 0.0996.
In other words, the rest of this problem is purely algebra.
Right.
I'm going to write it down below because I ran out of room. So that's f of a, right?
Right.
Okay. Minus, let me put parentheses around it. Excuse me, that's f of b, the first one. This is f of a, right? So far, so good?
Okay, yeah.
That's f of b minus f of a all over b minus a, which is 0.0996 minus 1. So, that's just a number. You can get that off your calculator or out of Wolfram Alpha or however you choose to do it.
Mm-hmm. Okay.
That's the answer. That's the average rate of change, whatever that number is. And I don't think we need to waste our time figuring out
the algebra, right? Yeah, I agree.
They're all in radians, incidentally. If you are using your calculator here, make sure you're in radians. Whenever you're talking calculus and trig, make sure you're in radians. Calculus, by the way, does not work the same with trig if you're in degrees. It doesn't work.
I found that out the hard way.
It only works if you're in radians.
Yeah.
So that's the answer to this one. When we do this one, all we do is substitute the different numbers.
Okay. Okay. And then as we do this, we'll start to get closer to a number, right? And
yeah, I'm not sure why there's such a discrepancy in these numbers. You would expect them to be getting closer and closer together.
Yeah,
In
that's the
fact, they're getting further and further apart.
I the problem is worded really poorly because it's there's 5 parts of question 1, and the first 2 questions have a table with it, but the last 3, this is problem C we're working on, are
Mhm.
just an equation, and it says where
Well,
t equals -1. So I wasn't sure if you're supposed to use one of these tables or you're supposed to just start creating intervals once you've plugged in
there's
-1.
there's the key right there. That
Okay.
is your key, what I've circled in blue. It's always f of b minus f of a, rise, over run, b minus a.
Okay.
Okay? So no matter what intervals they give you, this will always give you the average rate of change between those two intervals. Now, if they're trying to teach you calculus, then they would start with a wide range and go smaller and smaller and smaller, and maybe finally they would do 1 and 0.996, and you would get the idea that that rate of change approaches an instantaneous rate of change. When we finally do this one, we're getting much, much closer to the instantaneous rate of change. And that's the difference between calculus and algebra. Algebra is always about average rate of change. And
Okay.
this question is just about average rate of change. They haven't
Right.
quite taken you over the finish line yet to get to calculus.
Okay. Okay.
But
So
the only
then I
thing
think
you
this is a
need to
good
keep in mind is that's the way you always calculate average rate of change. What I've circled in blue on the left.
gotcha. Okay.
So
Noted.
no matter
Noted.
what interval they give you.
Okay. So I guess if we're talking about a limit in terms of concepts, we how would you describe a limit, I guess?
There actually is a pure, it wasn't stated officially until about 150 years ago, but there is a pure mathematical definition of limits called the delta epsilon. Hopefully you have not heard of this.
I have actually because I studied my dad's old college calculus book.
Okay,
But
well, if they are trying to teach you the delta epsilon definition of limits as a first calculus course, they are doing you a disfavor.
okay.
You want to demoralize somebody, try to get them to do delta epsilon definitions of limits. So let's not go there. And that's why
Okay.
I said I hope you haven't heard of it. But the fact you heard of it on your own is great. But they shouldn't be teaching you this in a first year calculus course.
Okay, cool.
Uh, Straight out of the lips of Saul Kahn. If you look at his delta epsilon 10-minute video, he will tell you exactly that. This should not be part of a Calc 1 course. So, the answer to your question as to what limits are, well, you can talk about them numerically and you can talk about them graphically. If I draw a graph of the hyperbolic function, half of it, and I say that's f of x, which is the notation you usually want to use when you're in calculus, not y, but f of x. Okay? And I say, what is the limit of f of x as x goes to infinity? What would you say?
Um, it's kind of hard to note, but I mean, I guess you could say it looked like 1,
0.
0.
In other words, this thing keeps getting closer and closer and closer and closer to 0.
Okay. Okay.
Okay? And on this end, it keeps getting closer and closer and closer to your f of x axis. So if I said, what's the limit of f of x as x goes to 0 from the right, which that's the only way it can go in this example, because I haven't drawn the other half of the hyperbola, you would say infinity.
Gotcha. Okay.
Positive.
F of x.
And you do need to distinguish between positive and negative infinities. So graphically, that's what we're talking about when we're talking about limits. Now, we could have a situation like this, where you have a function, and there actually is a horizontal asymptote. So whatever, if I call that f of x, and I say, what is the limit of f of x as x goes to infinity? If that was 3, that would be the answer. So it's not always 0, it's not always infinity, it's whatever. If you have horizontal asymptotes, that when you got introduced to horizontal asymptotes, you were actually being introduced to limits. That's what the function goes to as x goes to infinity, is it goes to that horizontal asymptote.
Okay. I want to dig a little deeper and just to piggyback off of this point. So let's say for example that the limit of f of x as x approaches say 2, and then also f of x equals 4. Is that going to explain that there's a vertical asymptote or a limit at 4?
So you're saying the function is 4.
Yes, the function is 4.
Okay, so let's graph that. What's that look like?
It should just be a straight line on 4.
Is it horizontal or vertical?
On the y-axis is horizontal.
It's horizontal. Like that. So that's that function.
Right.
Now, if you said, what is the limit of that as x approaches 2, what is it?
Okay.
Remember, it's always a two-step process. You always look at what, you get your stuff, your eyes looking horizontally, and you start going to 2.
Okay, so then it's
to 2, you look vertically at what f of x is.
Okay, so it's 4 then.
Yes.
Okay.
And
okay.
That's from the right side. What about from the left side?
So as we approach 2 on the left side, correct? It's still 4.
Yeah. In one case, we were doing this. In other words, in the first case, we were starting there and going there. And in the second case, we're starting here and going there. So when we're approaching it from the left, it's this case here. But in either case, that limit from the left is 4, and from the right, it's 4. And if we can prove that f of 2 is 4, then that will mean that function is continuous at x equal 2. That is the definition of continuity.
Okay, and that's for it to be a true that's for it to be a true statement.
That means it's continuous. All three of these things have to be true. In other words, the limit from the left has to be the same as the limit from the right, which has to be the same as the evaluation of the function at that point. And this limit definitely exists because it's the same from the left as it is from the right.
Okay. Okay, that makes sense. That makes sense. So, and this is just one more thing. I think this will be more of a I did want to jump into actually calculating limits, but one last
Sure.
question on,
We need some practice there. We haven't done much there.
yes, I agree.
I've introduced a few. I want you to give me some. The kind.
Okay, this is one last thing on still maybe defining a limit.
Uh-huh.
This question, for example, is asking given the piecewise function. This is Mr. Cohen, just as a side note.
Huh?
For programming, it's easy for me to understand what is being enclosed in a parenthesis. For some reason, in arithmetic, it just totally throws me for a loop.
Okay.
Okay,
Let's talk about. Tell me what
so
the piecewise function is.
yes, so it's the function is g of x, right? Or we can leave it as f of x.
All right.
I'm sure it's the same thing. So we have x with x being less or equal to -3. We have x squared with x being between -3 or less than -3 and less than 2.
Less than -3 and greater than 2.
Other way around, sorry. So -3 on the left side there. So let x is between -3 and less than 2.
I got you.
Okay,
Now
and
hold
then
on. Okay. No, I get you. Okay. Keep going.
okay, sorry. And then well, I'll just do one more. There's one after that, but these should answer the questions because it's 0 and then x equals 2. So the first part of the problem just simply states, I guess there's two that I wanted to just look at, but there's one that says g of -3. That's the
Okay.
first part of the question. So I just want to
Okay.
see, I just want to understand the tackle this.
Yeah, this is not calculus. This is still algebra.
Okay.
So g of -3. Which one do we use of the three that we're looking at?
The we use the top two,
Just the top one.
just the top one.
-3 is equal to x. In other words, you always want to start your analysis at the top right.
Okay. Okay.
Okay, -3 falls in this category, not in this category, not in this category. So you want to figure out where your number, which domain is it in?
Gotcha.
Okay, so it's in that top one. And when it's in that top one, it's equal to x. So that's equal to -3.
Okay. And then just
We're just going to plug in whatever is in the parentheses into whatever the function is.
gotcha. Okay. That answers that, at least one half of it. So then this is one more question for this. This will be the last one because they're all variations of these types. So this is the limit of x as x approaches -3. And then it's from the left.
Hold it. Is it the limit of g of x?
Well, yeah. So, well, hang on. So it's the way that it explains it. It's or shows it. It's the limit of x as x approaches -3 from the left, then g of x.
Okay.
If that makes
No,
sense.
I got it. It's just, this is a terminology problem.
Yeah. I mean,
What
that's
you really mean is, or what, the way to word this is, you're talking about the limit of g of x as x approaches -3 from the left.
from the left. Yes.
So that's the question, right?
Okay.
And that's the way to say it.
It's all on one line, so I apologize.
That's okay.
It's
I'm
not.
just trying to help you.
Yeah. No, I appreciate it.
How you talk in calculus mode. This is the limit of g of x, the function. What's the limit of the function? As x, the variable, approaches -3 from the left. Well, easiest thing to do here I don't know that we necessarily have to graph it, but let's do it. So if I go to -3, let's put my key points on here. And whenever x is less than or equal to -3, then it's equal to x, where that has a slope of 1, right?
Okay.
So I know that it goes from there, straight line, it's also linear, closed dot. So that yeah, hold on, I've drawn it incorrectly. Start it where, in other words, what is f of 3? Well, we know that f of 3 is -3. So that's -3 right there. And it's linear because it's y equal x. You with me?
I'm with you.
Okay. And now let's graph it between -3 and 2, just for the heck of it. Well, if I use this one and I said, well, what is f of -2.99999? I could approximate -3, and that's 9. So it's open circle there, and it's a parabola that goes like this. Since there's no equals on either one of those, it's open on each end. In other words, is all I'm going to do is graph a parabola between -3 and 2.
Okay.
Okay. And then it says that at x equal 2, it's actually equal to 0. So there is our piecewise function.
Okay. Okay.
Okay. And now, once you get a graphical picture of it, it's relatively easy to answer all of these questions.
Yeah.
In other words, this question, what's the limit of g of x as x approaches -3 from the left? So I have to hop on the, let me change colors here. I hop on the graph somewhere to the left of -3, and I start heading towards that point. So that point is clearly -3.
Okay. Okay.
And if I said to you, what is the limit of this function as you approach -3 from the right? Let's change it just marginally like that.
Okay.
So what's that value right there where I've put the blue horizontal line? Because that's what, in other words, I'm going to hop on board the function, right?
Right.
And I'm
then
going to
go
travel towards
the left.
-3 on the x-axis. And
Uh,
wherever I am pointing to at the very end, well, what is that point? Well, if I plug in -3, that point's 9.
Yeah.
What is this point right here? That's 4. And now I have everything I need to know. In other words, I can answer whatever limit question. Once I have that picture, now I can tell you what the limit of g of x is as you approach any of your key points from either direction.
Okay. Okay.
Actually, I can't approach 2 from the right because the function doesn't exist. It was not defined to the right of 2. Unless it was and we just didn't write it down. But to the right of 2 is outside of our domain as we have written it.
Okay. Okay, that makes sense.
if to the right of 2 was some other parabola like that, well, then we could go forth. And now we are going from negative infinity to infinity, which means we cover the entire spectrum of real numbers, and we can figure out all of these limit questions. But it has to be in your domain.
And I guess real quickly, I'm missing something actually now I'm looking at it. So how do we know that that point is -3? Yeah, no, hang on. So how?
Because that's not a less than or equal, and that's not a less than or equal, then these are both open circles.
Yeah, and how do we know at the second open circle? I get how the first one is 9. How is that second one 4?
2 squared.
Oh Jesus.
2
Okay.
squared is 4.
Okay, that makes we plug those in for that.
Yeah, even though it never actually reaches there, that's what you do. Even when it's an open circle, is you just plug in, just like we plugged in -3 for x to get 9.
Yeah. Okay.
We plug in 2 to get 4, even though it never actually gets to 2. In this part of the curve, never reaches 2. It just approaches it. When it actually gets to 2, it's 0. So f of 2 is 0, or g of 2 is 0.
Okay, that makes I appreciate it. That makes sense.
See that there's a lot of discontinuity in this.
Right.
That's because the limits from the left and the right are different in every single discontinuous place. Now, there is a layman's definition of continuity. It's if you don't have to pick up your pencil off the piece of paper.
Okay.
If I have to lift my pencil to draw a graph, then it's discontinuous. And to draw this graph, I had to lift my pencil. To get from there to there, I could not do it without lifting my pen. But
Gotcha.
that's not a particularly appealing mathematical definition. So this mathematical definition where the limit from the left has to equal the limit from the right, and they both have to equal the evaluation at that point.
Gotcha. Okay. Let's switch gears here, and we'll start working on some actual calculation. So this is these look ugly to me. So let's do one of these. As the limit of x approaches 3.
Okay, hold on. That's not the way to word it.
Okay.
We want the limit of some function. Remember, calculus is all about manipulating functions.
Okay.
I once heard let me just tell this to you briefly. A really great thing. Arithmetic is manipulation of numbers. Algebra is the manipulation of variables that represent numbers. Calculus is the manipulation of functions. Always remember that when you are talking calculus, you're talking about functions. So it's never the limit as x approaches. It's the limit of some function as x or t or whatever your variable approaches something.
Okay, perfect. I appreciate that. Let me try this again then. So the function now is the square root of x plus 1, and then outside of the square root is -2. And then that's all over x squared minus 9 with x approaching 3. Did I say that right?
As x approaches 3. So the way I would say that would be, what is the limit of the function whose numerator is the square root of x plus 1 minus 2 all over x squared minus 9 as x approaches 3. And that first of all, presumes that it exists, because it might not exist. Maybe as it approaches 3 from the left, it's not the same as approaching 3 from the right. Okay, but that's usually not the answer on these limit problems. What you're looking at here is the second method that we need to use in order to solve limit problems. I introduced you yesterday to the first method, which is factoring. This is not one that we can factor. And first of all, let's look at what happens if we just do a direct substitution.
Okay.
We get square root of 4, which is 2, minus 2, so we get 0 over 0.
Yeah.
So a direct substitution is 0 over 0, which they all are. If it's not 0 over 0, it is not a hard problem. It's not even a medium problem. It's an easy problem.
Right.
So the only ones you're going to be dealing with from now forward are the ones that are 0 over 0. So you can kind of skip that first step where you try substituting to see whether it actually produces a number. And it does not. It produces an indeterminable, which is 0 over 0. Now, I could factor the bottom. That factor is easy enough, x minus 3 times x plus 3. But that's not terribly helpful. When you see these limit problems where either your numerator or your denominator has a square root, a radical sign in it, then what you want to think of is, let's multiply that top and bottom by the conjugate. And what is the conjugate? It's x plus 1 plus 2. And since I can only multiply a function by the number 1, I have to do the bottom, x plus 1 plus 2.
Okay.
I'm now multiplying it by the number 1. And what's going to happen is, because I'm multiplying the numerator by the conjugate, it's going to get rid of the radical sign. That's what I'm looking to do. That's the secret, is to solve these, you want to get rid of the radical sign.
Okay.
So, if you'll notice, what the numerator is a minus b times a plus b. Right?
Mm-hmm.
I can consider this a minus b times a plus b. I know what that's going to be. That's going to be a squared minus b squared, right?
Right.
So a squared is x plus 1. Correct?
Correct.
No middle terms. Minus b squared is minus 4. So this times this is x plus 1 minus 4. Comes down to a very simple expression. I can condense that to x minus 3. Okay?
Okay.
And now the bottom is going to be x squared minus 9 times the square root of x plus 1 plus 2. You with me?
I'm with you.
And now let's try substituting again. What is the limit of that function as x approaches 3? The numerator still goes to 3. Excuse me, the numerator still goes to 0. The denominator still goes to 0 also. But notice that I can do something that is quite effective with the denominator. I can factor x squared minus 9. So I'm going to use a combination here. I'm going to erase that. with x minus 3 times x plus 3. And now I can start canceling. And when I draw a line like that, that means it's replaced with a 1.
Okay.
So now I have 1 over x plus 3 times the square root of x plus 1 plus 2. And now let's try substituting again.
Right.
And now you will get a number. You will not get 0 over 0. And the reason I know is because there's no 0 there. That's a 1. So if I substitute now, I get 1 over 6 times, I'm substituting 3 for x, 6 times 4. So 1/24.
Okay.
Okay, so this is a good problem. This is a medium hard limit problem because it involves not just factoring, but this concept of multiplying by the conjugate.
Right.
Which is really an important technique. That's the second technique to use besides factoring. And in fact, we had to use both. We had to not only multiply by the conjugate, but then we had to factor the denominator also so that we could cancel out one of these things. So eventually when we got down to this point, it was a factoring problem.
Right. Right.
And it did produce a number. A final number, not 0 over 0. And that's what almost always happens. And let me just tell you the third method, because there's only 3 that I know of. The third method involves trig functions.
Okay, I was gonna get there. As I was gonna mention another question. Okay.
And there are 2 limits that you have to remember. One is this one, and you have to memorize them because you don't have the math to know this yet. In other words, they can't teach you that until you get to that part of calculus. So they start out by telling you this is true. Okay, and the other one is this one. Notice that in both cases, if you substitute 0 for x, you get 0 over 0. Cosine of 0 is 1. So you get 0 over 0. This limit is actually 0, not 1. So start by memorizing these 2 things at the bottom right.
Okay,
and it can be 1 minus cosine x, same thing. The limit of 1 minus cosine x over x as x approaches 0 is 0. So you have to memorize that. And the reason you have to memorize it is because we can't prove it to you yet. But those are true statements. And once you accept that they're true, then you can use those for solving problems like I have on the upper left.
Okay.
So, you got these memorized so I can erase them?
Yep, I wrote them down.
Okay, those are the only 2 that they ask you to do that on. But it's hard to go further without using those 2 facts. So, if I want to figure out what this limit is, well, I don't have sine x over x. I got sine of 4x over x. But what can I do? I can take this function and multiply top and bottom by 4. Can I not?
Yes, you can.
Always multiply any function by the number 1. And 4 over 4 is the number 1. So now I have 4 sine of 4x over 4x.
Right.
And now this right there, what is the limit of that as x goes to 0?
Is it 1?
Yeah. So the total limit is 4. In other words, it doesn't have to be x over x. It can be 4x over 4x. It's just those two things that I just circled have to be the same. And whenever you have the limit of that, in other words, the limit of sine of square root of x over square root of x is 1.
Quick question, and I just want to know if I'm wrong here. So when I first saw that, you know, because I don't know the math, but assuming the logic of sine x over x equals 1, is it not fair to say that showing it as 4x over 1 is the same as saying it would be 4, knowing that sine x over x is 1?
If this is true, then this is true.
Okay, I see.
So whatever multiple doesn't matter. As long as this is the same as that. That cx is the same as that cx. That 4x is the same as that 4x.
Gotcha. Okay, that makes sense.
And the only way I was able to produce this was by multiplying top and bottom by 4. And then I have 4 times this thing that I know is 1.
Okay, that makes sense.
And those are the only 3 methods I know for doing limits, and they will absolutely solve all of your problems, those 3 methods. And those 3 methods, again, are factoring, multiplying the function by the conjugate. Sometimes you have to multiply it by the conjugate of the bottom, sometimes by the conjugate of the top. Depends on where your radical sign is. You multiply it by the conjugate of wherever your radical sign is. You understand what I'm saying?
Yes, I'm writing it down. Sorry.
Okay, here, let me just give you a couple of examples. If I have square root of x minus 3 plus 2 all over x squared, what am I going to multiply that by? If I'm going to solve this by doing the conjugate.
Right. So the square root of x plus 3.
Still minus 3 there.
Minus 3, okay.
The conjugate, the only thing that changes is that sign.
Gotcha, okay. So then minus 2.
And then I got to do the bottom by the same thing. So that's technique number 2. But I could just as easily have had x squared up there and square root of x minus 1 plus 10 down there. And now I want to multiply top and bottom by what?
The same thing on the bottom, right?
The same thing, the conjugate.
Okay, we got the conjugate.
So what is it?
So the square root of 1, or x minus 1, minus 10, top and bottom.
Yeah, there you go. That's all you have to know. And when you go through those, the reason you're doing it is because when I multiply that by its conjugate, I'm going to lose the radical sign. It disappears.
Okay, yep. And
that's what you're trying to do, is get rid of that radical sign. This is a very tough expression to deal with. So if you can get rid of the radical sign, you can see that it turns it into x minus 1 minus 100, which is x minus 101. In other words, it's a much simpler expression. So that's the second technique. And the third technique involves only this or this.
Okay, what we wrote down.
And that limit is 1 and that limit is 0. And so if they give you any limit problems involving trig functions, you're going to have to use one of these two.
And that would be, and that's true if, because I was going to ask, there's a problem that's the function is there's no fraction in it. So it's like I don't know if I'm saying this correctly, but the function is the quad root of 2 cosine of x minus 5.
And you said the quad root?
Yep.
Like that?
Like that.
And you want the limit of that as, hold on, let me see if I can tell you what is it?
As the limit approaches 0.
Okay, well, I don't think this is not a hard limit problem. This is a straight substitution limit problem.
Interesting, okay.
Okay, and the reason I say it is because it does not produce a 0 over 0. Always look for that. If you have 0 over x, that goes to 0. If you have x over 0, that goes to infinity. The only thing that ever gives you difficulty is 0 over 0 or infinity over infinity or infinity minus infinity. When you get to chapter 8, you'll cover all of these. But until we get there, the only ones you care about are 0 over 0. And this does not appear to be that. So if I do a direct substitution, then I have the quad root of, well, what's the cosine of 0 is 1. So now I have the quad root of minus 3.
And that's the final answer, the quad root of minus 3?
That's an imaginary number.
Right.
So that limit, this is kind of interesting. I'm not sure I've ever gotten one of these. Where they ask you for the limit of something that doesn't exist. I'm going to say does not exist for this. Even though it would be, there is an imaginary solution, but I don't know if they want that.
Okay. No, I was just curious because I was wondering since it's
the only I mean, other than imaginary solutions, and to be honest, I'm not sure how they treat that. Whether they want you to say do not exist or actually give whatever that imaginary solution is. What is that? That's minus 3 to the 1/2 times minus 3 to the 1/2. So that is square root of 3i times square root of 3i, which is the square root of minus 9. Which is 3i, maybe? So it's possible that 3i is the answer they're looking for? I don't know. I've never seen a limit problem that has an answer in imaginary numbers. It's on the fringe of limit theory. Let's just say that.
Okay. Let's
not spend our time on it because that's not what you're going to be faced with.
Yeah, no, that's fine. The actual key there was learning that I want to make sure that the answer isn't 0 over 0.
Exactly.
That makes
it's anything other than 0 over 0 or imaginary, then it's either in 0, infinity, or some number that you can come up with. What are called the indeterminable are 0 over 0, or infinity over infinity.
Gotcha.
And later on, they'll give you an extremely simple method. Let me just give it to you while we're talking about it. How would I actually figure out what the first derivative of that is? If that is y, then what is y prime? Well, it turns out that upon substitution, if you get 0 over 0, you can take the derivative of the top, and the derivative of sine is actually cosine. I don't know, have you learned these yet?
No, I haven't. This is
And
new.
the derivative of a function is just 1. And now if I substitute x going to 0, I can see that I have 1 over 1, which is equal to 1. It's called Lahapatol's rule. Where when you have 0 over 0, the simple way to do it is to take the derivative of the top, take the derivative of the bottom, and reevaluate. And when we do that, we get 1. So we've just proved that the limit of sine x over x as x goes to 0 is 1.
Okay, so if I heard you right, we just said, you just proved that an indeterminable actually can be solved for a limit.
Yes, and sometimes you have to take multiple derivatives. In other words, there are some functions where it starts out 0 over 0, and you take the derivative of the top, and you take the derivative of the bottom, and it's still 0 over 0. And you do it again, and it's still 0 over 0. And finally, at the 7th time you do it, you get 1 over 2.
Huh. Can you explain that some? Because you were showing that in the example yesterday of like getting the first derivative from something. So what does it mean to get like the first and second derivative and so on?
Yeah.
Or maybe
Let's
that's
talk about
actually
it mathematically first of all.
okay.
So there's our function. That means first derivative. Going to use the power rule. 4 times the coefficients, subtract 1. That's the first derivative.
Gotcha.
If I want to take the second derivative, that's the same as taking the first derivative of the first derivative. So it's really just taking another first derivative. It's just starting there. So it's 3 times 4. Subtract 1.
Or x squared.
And I can take the third derivative. And I can take the fourth derivative. I cannot take the fifth. Yeah, the fifth derivative is 0. But by the time I get to 0, I'm done.
Okay.
Now, what do all these derivatives actually mean? Well, in a physics connotation, the function is the position. This first derivative is the velocity. The second derivative is the acceleration. And notice what derivative means. It means rate of change. So here's our position. This is the initial rate of change of our position, first derivative. But what if I wanted the rate of change of the rate of change? Well, when you're in a car and you're going down the road, your rate of change is your speed. You are moving at 40 miles an hour. That is a first derivative. Your position is changing 40 miles every hour, right?
Right.
If I were to take the second derivative, I'm talking about the change in my velocity. If I go from 40 miles an hour to 60 miles an hour, I have to have accelerated. That's second derivative.
Okay.
And if you've ever driven with, I'll say it kindly, an old lady, because this is kind of the way my deceased mother used to drive, she drove as a third derivative, and that actually has a word for it called jerk. In other words, if you're driving down the road and somebody's constantly accelerating, stepping on the brake, accelerating, stepping on the brake, that's a third derivative. That's a rate of change of a rate of change of a rate of change. And there are no limit as to how many rates of changes you can have. You can have the 220th derivative. And that might not make sense to you yet, but let it just sink in. And so these multiple derivatives are part of calculus, a big part. It's not all about first derivatives. It's about second derivatives, third derivatives, fourth derivatives, and each one of them mean exactly what they're saying. This is a rate of change of the position. This is a rate of change of the velocity. This is actually a rate of change of the acceleration. And this is a rate of change of the jerk.
Okay. Okay. It's actually pretty cool. I like that.
And yeah, physics actually is the best thing to
relate this to.
Yeah, it really is, because everybody understands position, where your car is right now, and velocity, how fast it's moving, and acceleration, how fast it's accelerating. And that is the function, the first derivative, and the second derivative.
But I guess conceptually, a derivative would be change that you're trying to define from whatever context. So it could be as deep as many changes as you have.
Yeah, and you never go from nothing to second derivative. You always go first derivative, and then you take the derivative of that to get the second derivative, and then you take the derivative of that to get the third derivative. So getting all of these higher power derivatives is not hard, it's just laborious. You have to step through it.
Right. Okay. No, I like that. That's actually pretty cool.
And this power rule makes it doable. In other words, if you had to figure out the fourth derivative, let's say I have my function is x to the fourth, and I want the fourth derivative of that, and I had to do it by using the quotient definition, f of x plus h minus f of x all over h, it would take forever. Whereas by using these power rules, it's really easy to get the first derivative, the second derivative, the third, the fourth, all the way down to 0.
Okay. I think honestly we'll touch back on this. I haven't learned about it per se, but
here's something that's worth knowing for you. Oddly enough, the derivative of the sine is the cosine. And just to kind of demonstrate why that's true. The blue is the red is the cosine curve. The blue is the sine curve. And what I'm actually saying is that if I look at the sine curve and I look anywhere along that curve, what's the slope? It's the cosine. If I look at the slope at that point in time, if I'm looking at the slope of the tangent line, it's 1. It's right there. You with me?
Okay, okay.
If I get up to pi over 2, what's the slope of that tangent line?
It's 1.
No. What's the slope of a horizontal line? 0.
Oh, it's 0.
Yeah. That's what that is. It's the cosine.
I see. I see.
If I
Okay.
get over to here, what's the slope there? It's -1. In other words, so the cosine truly is the derivative of the sine. And you can prove it by just going along a sine curve, looking at the various slopes, and realizing that they match up perfectly with the cosine curve.
Okay.
I get back to here, slope of the tangent line is 0, cosine again is 0. I get to here, slope of the cosine curve is 1, the value of, or excuse me, slope of the tangent curve to the sine curve is 1, the value of the cosine curve is 1.
Mm.
So, hold on, I'm not quite done yet. This is key for you to know. This actually is key for a lot of really higher calculus. If I look at the second derivative of sine, it's just the first derivative of cosine, which, believe it or not, is minus sine. And the third derivative of sine is minus cosine, because I'm just taking the derivative of that. So the derivatives of the trig functions are very important to memorize. You want to know what the derivative of sine is, you want to know what the derivative of cosine is, you want to know what the derivative of tangent is. If my function is tangent of x, guess what? Y prime is secant squared.
Okay.
In other words, the derivatives of trig functions are usually trig functions, which is surprising. You wouldn't, I mean, that's like a revelation. Who would have guessed that the derivative of the sine is exactly the cosine? If you go and measure each slope, it turns out to be the measurement of that slope is the value of the cosine curve. And the derivative of tangent of x is secant squared of x.
Okay. Okay.
So there will be some considerable memorizing, just like in trig, where you had to memorize like 50 things, right?
Right.
In differential calculus, they're going to ask you to memorize the first derivatives of your 6 trig functions, and also the first derivatives of your 6 inverse trig functions. For example, if my function is inverse tan of x, y prime is 1 over 1 plus x squared, oddly enough. When you take a derivative of an inverse trig function, you get an algebraic answer. That's algebraic. That's not a trig function. So when you take derivatives of trig functions, you get trig functions. But when you take derivatives of inverse trig functions, you get polynomials.
Mm.
And they're going to ask you to memorize those 6. So there's going to be 12 critical things that they're going to ask you to memorize, which is the first derivatives of all 6 regular trig functions, and then what's the first derivative of all 6 inverse trig functions.
Okay. Okay.
Okay? So be prepared for that, and once you do that, that's going to make the rest of trig a lot more understandable, and trust me, differential calculus is really easy because you can narrow it all down to these 4 rules. The power rule, the product rule, the quotient rule, and the chain rule. Have you Has anybody demonstrated any of them to you other than the power rule?
Let's see. The quotient rule, yes.
That's the harder one. The power or the product rule is a
And the
little bit.
product rule.
Yeah,
Yeah.
if I said I have two functions, that's one of them, that's another one. So I'm looking at kind of a composite function here.
Mm-hmm.
And let's call this, they frequently use the letters U and V. So if I wanted y prime here, I don't have a product rule that I can use because I've got the product of two different kinds of functions. But what it ends up being is u prime times v plus the opposite, u times v prime, and that's it. Okay? So
Okay.
if I wanted the derivative of this function, well, u prime is 1. The derivative of x is 1. V is sine x plus u, which is x, times the derivative of sine x, which we know is cosine x. That's the answer. And notice that it's a little harder than just the product or the power rule. The product rule requires you to do that.
I was just gonna say you make it seem all so easy, but
Well, the product rule is. The
fair enough.
quotient rule, let me just introduce you to that. If I have two functions being divided like this, then y prime starts getting really complicated. You start with the bottom and end with the bottom squared, is the way I remember it. What does that mean? I start with the bottom. I'm going to multiply it by the derivative of the top. And now there's subtraction going on. So order is important, and I do the opposite. So v prime times u. And you end with the bottom squared. So there's your quotient rule.
Okay.
And if I had x divided by sine x, this is what I would use. So I've given you three really important tools in differential calculus, which is the power rule, the easy one, and then there's the product rule, semi-easy, and then there's the quotient rule, tough to memorize, but not if you use that little meme that I just said. You start with the bottom, and you end with the bottom squared.
Right. Okay.
And if I'm starting with the bottom, what goes next to it has to be the derivative of the top. And then also remember that subtraction is what's going on, not addition. Notice that in the product rule I had addition. In the quotient rule you have subtraction. And then just do the opposite. If the first one was v times u prime, then the second one is v prime times u. And it's all divided by the bottom squared. So there's your power, product, and quotient. The only one left is the chain rule. And it's probably more than we want to tackle today. But it's what comes next. And between those four rules, you can differentiate anything. I could have something like this. Doesn't matter how complicated. All cubed. And between those four rules, I can differentiate this. The four rules being the power rule, product rule, quotient rule, and chain rule. All of them would be required to differentiate this function. Remember, calculus is a process on functions.
Right. Okay.
Always doing something to functions. Differential calculus, your differentiating functions. Integral calculus, your integrating functions. Integration is just the inverse of differentiation. You've learned inverses, so you know what inverses mean. That's the difference between differential calculus and integral calculus. They're just inverses. And oddly enough, they were invented separately before they realized that one was the inverse of the other. Newton invented differential calculus, Leibniz invented integral calculus, and 30 years later they realized one was just the other side of the coin of the other. And that's probably a good place to stop. I could go on forever. So.
Yeah, I appreciate the passion. I also appreciate the information. Actually, one of the things that bothers me about math is that you don't get a history of how it came to be. They just kind of throw you in the water, you know.
Yeah. Actually, the
Calculus is
history
actually,
of calculus is one of the more interesting history of maths. It really is.
yeah.
They say the most important book ever written in math was Sir Isaac Newton's Mathematica, which he published in 1680. Well, guess what? He had already discovered calculus and did not include it in that.
Huh.
Because he wasn't certain of it. It had this weird concept of division by zero or division by things that approach zero. And so he was as skeptical as anybody else. And so here was, he had made the most important discovery in all of math history, and he didn't even include it in the book that is now considered the best math book ever written. And he could have put it in there. He didn't because he wasn't sure of himself. But once Leibniz invented integral calculus and they got together and they realized, wow, these are just inverses of one another, and this is a true new approach to math, and history changed because calculus allows us to do so many things that we could not do without calculus.
Right. Right. All right, Mr. Cohen.
All right, Connor.
I appreciate your time as always. I will I'll email, or I guess I'll contact you when I need to get a hold of you.
Sounds good. All right.
Have a good one.